Hi everyone. Today we will discuss about optimization. The objective of this subtopic is to solve optimization problem from a wide variety of fields using first and second derivative. Okay, so in this subtopic, we will focus on how to solve general optimization problems. We will also look into the optimization in area and volume, as well as optimization in business. There is no new concept in this subtopic. However, we will review some of the important concepts before we start. Okay, so the first concept is, we know that local maximum and local minimum happens when dy dx equal to 0 or when first derivative equal to 0. Okay, and then the second concept is we need to know how to verify whether we have maximum or minimum value. So the first method we use is second derivative test. So we know that if second derivative is more than 0, we will have minimum value. If second derivative is less than 0, we will have maximum value. Okay, the other verification method is to use sign test. We will look at two examples. So in example number 1, we need to find two positive numbers, x and y, whose product is 48, such that 3x plus y is a minimum. Okay, so based on the question, we know that the product of x and y is 48. So we have x times y 48. Okay, so we put y in terms of x. So we have y equals to 48 divided by x. So this is our first equation. Okay, so based on the question, we know that we wanted the 3x plus y to be a minimum. Okay, we let the value of 3x plus y be v. So we will have v equals to 3x plus y. Okay, so since there are two variables here, so I substitute y with 48 divided by x into the equation. So now I have v equals to 3x plus 48 divided by x. Okay, so I change the fraction into index form. Okay, so now I can do my differentiation. So because we need to, we know that first derivative equal to 0, then we will have maximum or minimum. Okay, so I do my first derivative, differentiate the v with respect to x. Okay, now we have dv dx. So we need to equal dv dx to 0. So, okay, we have an equation that we can solve. Okay, we can solve this equation to get x. So we will realize that x squared is actually 16. And then what is x then? Okay, x will be positive, negative, square root 16. And x is actually positive, negative 4. Okay, if we go back to the question, x and y is positive number. So that means we have to justify that because x has to be positive or x has to be more than 0. Therefore, x must be 4. Okay, we only accept x equals to 4. Okay, next we need to do a verification. Okay, is it true that when x is 4, we will have minimum value? Okay, so we need to find out the second derivative. Okay, just let me copy the first derivative. Okay, so I differentiate dv dx one more time. Okay, so we have d2v dx2 equals to 96 over x cubed. Okay, so when x is 4, second derivative is equals to 96 divided by 4 cubed. And this value is actually more than 0. Okay, when second derivative more than 0 means we have minimum value. So we know that 3x plus y is minimum when x is 4. Okay, so the next step is we need to find the y value. So when x is 4, the y value is 48 divided by 4, so we get 12. So finally we say 3x plus y is minimum when x is 4 and y is 12. That's all. Okay, there is another example. Okay, so there's one more example in regarding optimization. So okay, in this example number 2, there is this rectangular sheet of cardboard measuring 16 cm by 10 cm. Is to be formed into open rectangular box by cutting out identical square from each corner and folding up the sides. What size must the square be for the box to have the maximum volume? Okay. So first of all, okay, we have a rectangular box like this. So the length is 16 cm, the width is 10 cm. Okay, so we know that we have to cut the square at the corners. So the green part represents the corner that we need to cut out. Okay, so at this moment we do not know the side of the square. Okay, so we can let it be x. So in this case, the side of the square is x cm each. Okay, so imagine if after you cut out the square, then you fold the cardboard, okay, then we will have a box. This is an open box. Okay, so the open box will have the height of x cm. The width is 10 minus 2x cm, and then the length is 16 minus 2x cm. Okay, so we know that in the question we need to maximize volume. Okay, so we need to find the formula or function for the volume of the box. We know that volume is the width times the length times the height. Okay, so the width, okay, we substitute the width, the length, and the height. Okay, so we have the function for the volume. Okay, then we ask ourselves, what is the x value that will make the volume to be maximum? Okay, so the next step is we need to find the x value. Okay, how do we find x value? First of all, we need to differentiate the v with respect to x, yeah, to find the first derivatives. In this case, we get dv dx. Okay, so this is our dv dx, and we need to equal it to 0 because we know that local maximum and local minimum happen when first derivative is equal to 0. Okay, so when I solve the equation, I have 2x value, x equal to 2, and also x equals to 6.66667, or it is actually also equals to 6 and 2 over 3 cm. Okay, so now we have 2x value. So which value will make the volume to be maximum? Okay, so in this case, if we substitute x equals to 6.67 into the length, into the width, yeah, the width of the box, we will get negative value. So automatically, this value is rejected. So x is equal to 2. But how do we do a verification? By using calculation. Okay, so we do the verification by using the second derivative test. So we find out the second derivative. Okay, And so now we substitute x equal to 2 into second derivative, and we realize that second derivative is negative 56, which is less than 0. And when the second derivative less than 0 means we have maximum volume. So it is confirmed that when x is 2, the volume is a maximum. Yeah. So the square must have the side of 2 cm for the box to have a maximum volume. Okay, next, try this question on page 57 in the manual one. Okay, so all the best. I will see you in class soon.